Yay. All right, here we go. All right, so firstly, everyone hopefully has the next assignment, and we'll have our usual problem session on Friday. All right, so last time we were looking at the problem, we were solving the problem of spin magnetic resonance. We're solving that in the Schrodinger picture. Okay? So the problem is the one we've been looking at for the last few lectures, where we have a magnetic dipole, spin magnetic dipole, in a magnetic field. It has a Larmor precession rate that's determined by the strength of the magnetic field, B naught. And we want to flip the spin, and by applying a transverse field that is oscillating, in this case rotating, at some frequency omega, that will cause the spin to flip at the Larmor rate, capital omega, also known as the Rabi frequency. And we can solve that as well in the Schrodinger picture by just looking at the Schrodinger equation. So we have the Hamiltonian, which is in this case time dependent, and we can think about this in a spirit similar to what one often learns in quantum mechanics in terms of time-dependent perturbations. So we can imagine, we can break this Hamiltonian up into an H0, which is related to this, the interaction with the static magnetic field, which splits out the energy levels of spin up and spin down, with the negative gyromagnetic ratio. Spin up is along the positive z direction, and a time-dependent interaction which is driving the system and wants to cause absorption or emission. And so this field is oscillating at the frequency of the drive. This we can call the resonance frequency, when that's related to the Bohr energy, which is to say the energy difference between the excited and ground state. There is the difference of those energies by the h bar is a frequency, which is omega naught, and we're driving it at frequency omega. Yeah.
So all of the stuff that we talked about here feels very, very physical. Like a B field and then a spin and
Yeah.
a rotation.
Yeah.
But this is still all true, like you said, for any two-level system.
It is. So we'll re-emphasize that fact very soon. Today, we'll start talking about the two-level atom, where that then becomes a pseudo-spin. So this is an actual physical problem, and one that we use all the time in NMR, in MRI imaging. This is an actual physics thing. There is a physical spin, it's pointing in a physical direction and physically moves, and this is its dynamics. However, as you very rightly and importantly emphasize, as we'll see, all two-level systems are isomorphic mathematically to this, where in that case, the block sphere we're talking about is an abstraction. It's not the actual physical directions of things, but a mathematical mapping of the state of the system in terms of these block vectors, which are abstractions, okay? And we will see there's various ways where that gets confusing, and I'll try my best to sort of separate out some of those things. But thank you for making that point, because it's really important. Okay, so what we did last lecture, is that we want to solve the Schrodinger equation. And we solved the Schrodinger equation. In general, the solution is difficult. In general, if I have a time-dependent Hamiltonian, in general, there is not an easy closed form solution to that, because I can't just exponentiate the Hamiltonian. There's this time ordering operation, which is messy and confusing and hard to deal with, and generally not a problem we can generally solve. However, in this case, we can solve it exactly by going to, in the same way that we did in classical mechanics, we go into the frame that's co-rotating with the field. In that case, we have a static field, and then we can solve the problem exactly. So to go to the frame that's co-rotating at the frequency of the drive, we apply the rotation operator that is associated with a rotation by that angle, okay? And in the rotating frame picture, or picture frame, we relate that to the Schrodinger picture by the dagger, okay? Because we're doing that's a passive rotation. We're changing the basis as opposed to moving the vector. And when we plug this into this, what we found, importantly, is that the Schrodinger equation in the rotating frame picture looks similar, but with a transformed Hamiltonian. And the transformed Hamiltonian is the rotated Hamiltonian, and then by Larmore's theorem, which comes out without, by just plugging this into here, we have that there is this additional fictitious magnetic field because we're in the rotating frame, right? That's like the Coriolis force in classical mechanics. And so when we plug all of that in, what we found is that the Hamiltonian in the rotating frame now is time independent. It has a z component and an x component by the choices that we've made, where the z component depends on the detuning. The detuning by convention that we will always choose is the drive minus the resonance. So the detuning is positive if I'm above resonance, so-called blue detuning, and negative if I'm below resonance, so-called red detuning. And the Rabi frequency is proportional to the strength of the transverse field. And so this is the Hamiltonian in the rotating frame. And given that, we have the solution, which says that the time evolution of this quantum state in the rotating frame is, we can just exponentiate the Hamiltonian now. Because it's time independent. And because it's time independent, I don't have to worry about time ordering, or the fact that it doesn't commute with itself at different times, and all of the problems that we have. We just do it, okay? And so this is the time evolution operator in the rotating frame. In the lab frame, we have to put back the rotation, so, this thing is rotating around, okay? Okay, so this time evolution operator then when I plug that in, is this. I'm sorry, that's the effective, too many subscripts. Right? That's the time evolution operator, okay? So let's take a good look at this thing again. So let's consider the case that I'm on resonance. On resonance means the detuning is 0. That is to say, the drive frequency is equal to the resonance frequency. Then in that case, delta is 0. And the time evolution operator then takes the form e to the I omega t over 2 sigma x, right? When delta is 0. So what is that operator? Well, that's the rotation operator that rotates me around the x-axis by what angle? Omega t. Not omega t over 2, but omega t. Okay? The 2 comes from the fact this was spin 1/2. And so what this is, we know for spin 1/2 we can rewrite this like this. That's true for the way we can expand this out, right? And so if, for example, at time t equals 0, we're in the ground state, which in this case is spin down, then what is the state at a later time? Well, we just can write it out by applying the time evolution operator, at least in the rotating frame. We can go back to the lab frame, should we choose, and that's cosine omega t over 2 spin down minus I sine omega t over 2. Sigma x acting on this is what? Spin up along z, because sigma x is sigma plus sigma minus. Right? So what this tells me is that the probability to be spin up as a function of time in units of the angular frequency undergoes Rabi oscillations. This probability is the square of this amplitude, which is 1 minus cos omega t over 2, right? So we have Rabi oscillations, which we can understand in this case if this is the x-axis on the block sphere as the system rotating around the x-axis with a torque vector that is frequency, and it Rabi oscillates, means Larmor precession on the block sphere at the angular frequency capital omega, okay? So it starts here along the z-axis, and then when this is equal to pi, then it's on the north pole, right? Because when omega t is pi, sine pi over 2 is 1, and that's spin up. Now, of course, we have this overall phase, but that doesn't affect the probability, okay? If I am and that's, as we said, that's called a pi pulse. And that's the kind of picture we might think about when we think about absorption, when we say, oh, I started in the ground state and I need a quantum jump to the excited state. But that's really not the right picture you should have in your head associated with coherent dynamics. The system is continuously evolving, and the state of the system at all times involves some amplitude, probability amplitude to be in the ground or the excited state. And intermediately, before I get to this point, I have some probability to be in the ground and some probability to be excited. And I'm in a coherent superposition thereof. And at this time, I have an equal superposition of being in the ground and the excited state. That's a pi over 2 pulse, and that would correspond to rotating this thing and putting the block vector in the equator on that pole. And when that's pi over 2, then this is pi over 4, then this becomes 1 over root 2 spin down along z minus I 1 over root 2 spin up along z. Which is a spin pointing along what direction? Well, you gotta be really careful.
Spin along x.
No, it's not along x, you've got an ion here. But the way we always write it is we make the thing in front of this real. And then the phase, so we gotta factor out the phase, right? This then becomes minus I spin up along z plus I spin down along z, which is spin up along y, which is what it should be, right? Because y is into the board, x, y, z. So that all makes sense, okay? All right. I should mention that, let's go back to this picture over here. The way I've chosen this magnetic field was somewhat arbitrary to be along the x-axis at time t equals 0. In principle, I can think about it being along some other direction at time t equals 0 to be somewhere in the xy plane. This is some phase. Okay? So, what would change in that problem? What would change in if I had chosen my time-dependent field to be oscillating around the same way, but at time t equals 0 to be somewhere in the xy plane with an angle phi, a phase phi? What would change in that case? Well, what would change in that case, the only thing that would change in that case is that instead of this being sigma x in the rotating frame, it would be that. Okay? So if I had the arbitrary phase, it would say that on resonance, the axis of the torque is not the x-axis, but this axis, okay? So I can call this thing perp as a function of phi, where E perp as a function of phi is a perpendicular, some vector, a unit vector in the xy plane that is rotated by angle phi, okay? If I had a phase in there. And in that case, what would change here? Well, in that case, this would be that. Okay? So, if I draw this picture over here of the block sphere, I'm going to draw it in a slightly different way. So here's the x-axis, here's the y-axis, here's the z-axis. Then actually, I can't draw perspective very well. So this is gonna be the x-axis, and the y-axis is gonna be to the board, okay? So if I had some phase in the problem, then it says that I don't torque around the x-axis, but I would torque around this axis on resonance. And so if I started down here, I have an oscillation. Let's see how I want to draw this. Terrible. Let me see if I can try. So I've got to rotate this circle here that is perpendicular to E perp. Right, so here's E perp, and so before I rotated like this, and now I have to rotate this circle, right? That is, so it's processing around this axis. You guys are gonna have to help me with better art lessons, but I hope you get the point, okay? So, we can now write down the general solution. Okay, so the general solution, we have that the state at time t in the rotating frame was e to the minus I h effective, omega effective dot sigma. Now, omega effective minus delta Ez plus omega E perp. When phi is 0, this was the x-axis. When phi is pi over 2, it's the y-axis, okay? And I want to find the solution to this problem where this, say, starts in the ground state. How can I do it? Well, I can write this vector as having a magnitude and a direction. The magnitude of this vector is what? Given this. I can't, some people are mumbling. I won't watch you tell me. Tell me.
12 plus omega squared.
Thank you. Right? That's the magnitude of that vector. Okay? And its direction is, well, minus omega over h effect, or omega effective in the z direction, plus omega over that magnitude in the perp direction. Okay, so that's the okay. So given that, I can look at this time evolution operator as e to the minus omega effective t times the Pauli in that direction, right? But I can write that this is a Pauli in some direction. Maybe it's the x direction, maybe it's the y direction, maybe it's got some z component, but whatever it is, it's in some direction. Any such rotation operator has the same form as what we wrote down over there. This is cosine of that angle over 2 times the identity minus I sine omega over 2 times the Pauli in that direction. Is that clear? right? It doesn't matter what direction this is some angle, that's always the form. If I have e to the minus I theta over 2 times some Pauli, it has that form, right? And this is what? Well, this is equal to minus delta over the magnitude sigma z plus omega effective cos phi sigma x plus sine phi sigma y.
Sigma Z in the front, right?
Sigma z. Right? I just took the dot product of this unit vector with the Paulis. It has a z component, and it has a transverse component like this. Stare at that for a moment. Now this I can rewrite in terms of the raising and lowering operators, because sigma plus and sigma minus, I have sigma x and sigma plus plus sigma minus. So I can rewrite this with a little bit of algebra as e to the minus I phi sigma plus e to the plus I phi sigma minus. Just rewriting the Pauli x and Pauli y in terms of the raising and lowering operators. Okay, just a little bit of algebra to show that. Okay, let's put it all together now. That's the time evolution operator. So now we have the general solution. The time here, the state in the rotating frame is this acting on the initial state, which is spin down. So what is the state at a later time? Well, I applied this rotation operator to that, and here is a lovely way of writing the rotation operator in terms of the identity and the Paulis. So now we can just apply this operator to the state, and what do we get? We get cosine omega effective t over 2 times spin down, that's the first term, minus I sine omega effective t over 2 times the minus detuning over omega vector. Sigma z acting on that is what?
Negative.
Right. So I'm going to get plus spin down over z. That's the first term, right? Because when sigma z acts on spin down, I get minus 1. Then I get plus omega over omega effective e to the minus I phi sigma plus acting on this is what? Spin up. Plus e to the plus I phi and sigma minus acting on that is what? 0, so forget it. Okay. So let's put it all together. What do I have? I have cos omega effective t over 2 minus I e to the minus I phi sine, I don't know what is this, omega over omega effective sine omega effective t over 2 spin down minus I e to the, let's see, did I get that right? No, I didn't. Minus I delta. That's right. Then I have minus I e to the minus I phi. We did it. It was kind of complicated, but not really once we get a little bit used to it. We have the general solution now to the solution to the Schrodinger equation.
There's no phase factor in the second term.
Did I do something wrong?
Just the phase factor in the second term.
Should be e to the I phi.
Shouldn't be there.
The second, this guy's not here.
Yes.
Thank you. Thank you, Shri. Okay, good. So, this is the general solution. We solved this in the Heisenberg picture more easily, but in the Schrodinger picture, this is what the amplitudes are, okay? And this is representing Langmuir precession around some axis. If we wanted to, we can calculate the block vector as the expectation value of sigma x, sigma y, sigma z, and we would see this very same thing. But this is a different representation of the same thing in terms of the amplitudes in spin up and spin down. Okay? So with this, we can just, again, say, what is the probability to be in the excited state? Okay, so, well, I guess there's a few things I want to say here. So, let's say we're on resonance. We're on resonance. Then what do we have when we're on resonance? We're on resonance, omega effective is omega, delta is 0, and the state at a later time is cos omega t over 2 spin down minus I e to the minus I phi spin up along z times sine. Or equivalently minus e to the minus I e to the minus I phi sine omega t over 2 spin up plus I e to the I phi cos omega t over 2 spin down. Right? Factoring that out. So what can we say about this? Again, the probability to be, if I'm on resonance, regardless of this phase, the probability Rabi oscillates. So if I'm on resonance and I look at this as a function of time, as we wrote before, we get Rabi oscillations at a period omega t is 2 pi, and it goes all the way up to 1. However, the phase of the drive determines the relative phase when I make a pi over 2 pulse. So if the phase is 0, I'm rotating around the x-axis, and at a pi over 2, I'll be spin up along y. If the phase were pi over 2, then I would be rotating around the y-axis, right? And if I rotated around the y-axis, this would be a minus 1, which would be what? If this were I, if this were pi over 2, that would be I times I, which would be minus 1.
Down along x.
It would be down along x. which if you think about the right-hand rule is right, if I rotate around y, and so the relative phase, now, I wanna ask you, do we care about this phase phi?
Yeah.
Yeah, we do, because it depends on it tells me something about the relative phase. This overall phase we don't care about. What would we choose it to be? What phase would we choose it to be? Well, we would typically call it 0 unless we had a reason to do otherwise. And why wouldn't we have a reason to do otherwise? Well, we might have a succession of pulses. I might have one pi/2 pulse, and then a second pi/2 pulse. And if my second pi/2 pulse has a shifted phase relative to the first, in the first case I might rotate around the x-axis, but in the second case, I might want to rotate around the y-axis. So the guys, the folks, the gals, everyone in the lab, you got to keep track of your phase. You got to have your local oscillator oscillating, because if your next pulse isn't in phase properly with the first pulse, you're rotating around a different axis. Okay? So you've got to always keep track of that phase. Coherent control requires you to really lock the phase of your oscillator, and that's what's really hard with the laser, because it gets out of lock all the time. Microwave's much easier. All right. Now, if I'm off resonance, well, off resonance, what's the probability to be in up as a function of time? Well, it's this probability. Which according to this expression is what? What is the probability to be spin up as a function of time? It's the square of this amplitude, right? Which is equal to omega squared over omega effective squared sine squared omega effective t over 2, right? Which is equal to omega squared over omega squared plus delta squared times the sine of the square root of that over 2, which is 1 minus cosine of that. So what that would correspond to is something which oscillates faster, and the maximum probability to be in the excited state is not 1, but is this ratio. Yes, Nate, you have a question?
Sine squared.
Sine squared. Thank you very much. Right? And that's off resonant, which I drew an example thereof over there. Okay? And the axis of rotation depends on the strength of the Rabi frequency, the detuning, and the phase of the oscillator. Okay, very good. This is really important. I mean, you got all this piece, to really understand just sort of the essence of how we manipulate qubits. It's this. And it's all just about Balmer precession. All right, good. Now, I want to still keep our focus on this problem. We solved the problem by just finding the time evolution operator. But we can also think about this in terms of the eigenvalues and eigenvectors of the Hamiltonian in the rotating frame. Okay, so let's think about the eigenvalues and eigenvectors. Oops. Okay, so I asked, all right, this, again, I can rewrite it. It's minus delta over 2 sigma z plus this cos phi sigma x plus sine phi sigma y. This is the Hamiltonian. I ask you now, what are the eigenvalues and eigenvectors of this Hamiltonian? How would you find them? Yeah, we would diagonalize the Hamiltonian. Now, how do you diagonalize the matrix? Well, the way you learn it in some of your other classes, you write down the secular equation, and then you find the roots of the polynomial. No. Not for spin 1/2. You should never, ever do that. Why? What do you think?
Because you can take the trace and get the block vector.
That's right. And so let me ask you a different question, a similar question. Suppose I had the following Hamiltonian. What are the eigenvalues and eigenvectors of this Hamiltonian?
Plus minus.
The eigenvectors are up and down along y. And what are the eigenvalues of this?
Plus minus h bar.
Plus or minus h bar omega over 2. Okay, I ask you now, what are the eigenvalues and eigenvectors of this Hamiltonian? Up and down along what, some direction. So the eigenvectors of this are spin up along the direction of that, and spin down along that direction, which is somewhere. We'll come back to what that is, because as Nate correctly said, we really should think about the block vector, but we'll come back to that. What are the eigenvalues? That's much easier than what the eigenvectors are. What are they?
Plus and minus h bar omega factor
That's
over
it.
Plus or minus h bar, the magnitude of that vector. So the eigenvalue is plus h bar and for spin down, it's that. Ta-da! We diagonalize the matrix. Dun, 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 dun. Did I do the happy dance? We didn't have to do any. We just look at it. If we can write the thing as something in some direction, then it's spin up and spin down along that direction with eigenvalues plus or minus that. We diagonalize the matrix. So I'll come back to the eigenvectors. Let's talk about the eigenvalues. Let's write down what the eigenvalues are as a function of delta. Okay? So if I were to look at what the eigenvalues are as a function of the detuning, okay, then these are hyperbola, right? So when delta is 0, the eigenvalues are plus and minus h bar times the Rabi frequency, right? When delta is really, really big, the eigenvalues are plus and minus delta over 2. So what we have is something that looks like this. Okay, so at delta equals 0, the splitting is h bar times the Rabi frequency. When delta is huge compared to the Rabi frequency, the eigenvalues are plus and minus the strength of the detuning. we can think about this again as if I called this H0 and this the interaction term, then I can think about these dotted lines as the eigenvalues of the bare Hamiltonian without the drive. Without the drive, this was the bare Hamiltonian in the rotating frame. Remember, H0 was h bar omega naught over 2 times sigma z, and then we turned on the drive. This is what we call the bare states, and they are minus delta, so what that means is that for red detuning, this is spin down, and this is spin up along z. When I'm very far detuned, this dominates. And what I would have is spin down, and on the blue side, this guy goes through, and this becomes spin down, and this becomes spin up on the blue side of the. So these dotted lines would be in the absence of drive, and this is just. It's a little confusing. These dotted lines represent the eigenvalues in the rotating frame. And in the rotating frame, what is the ground state and what is the excited state looks different depending upon which side of red is, because this is minus delta, right? So on the red side of detuning, spin down is the ground state and spin up is the excited state. On the blue side of detuning, very, very far from resonance, it's the opposite. Yeah.
What if I'm very close to resonance?
Well then, that's, so I have something else. So firstly, let me ask you, what if I'm exactly on resonance? Okay, let's, for simplicity, take the phase to be 0. We'll come back to the phase, that makes it more complicated. So that's a good question. What if I'm exactly on resonance? What are the eigenstates? So when delta is 0, what are the eigenvectors of this Hamiltonian? Spin up and spin down along what direction? X.
Okay. Yeah, because
Spin up and down along X. So the eigenvectors here, when I'm exactly on resonance, and spin up along X is that, and spin down along X is that. Okay? So, the instantaneous, the eigenvectors as a function of detuning are different. Okay? There's a, oh, that's why these things are here. That was very smart. I would have thought of that. Right. We can think about this, and this is a hint for your extra credit problem 3. Here's the block sphere. Here's H omega effective for an arbitrary detuning. The eigenvectors of the system are spin up along this direction, and spin down along this direction. Those are the eigenvectors for a given omega. Now, if I'm very far off resonance, then I have a huge z component and a tiny transverse component, which means omega effective is along that direction, and the eigenvectors are spin up and spin down along z. If I'm on resonance, then my eigenvectors are spin up and spin down along, say, x or y or whatever I am in the transverse direction. Okay? And so if I take, here's my two-level system, I'm well below resonance, say, to start. So far, but if I sweep the problem through resonance, I adiabatically follow one of these curves. And we can understand that if you think about precession around, normal precession around omega, if I'm changing the direction of that, I can adiabatically follow. It's a lot of words. We'll think about that a little bit more, okay? Let's solve for, I ask you now, what's the general solution to this problem? Even for an arbitrary phi, I want to know what are the eigenvectors of the problem when I have an arbitrary detuning and an arbitrary phase? Well, they are spin up and spin down along some direction. And everyone did problem set 1 knows how to express spin up and spin down along some direction. So if I have some direction in space, and I want to know what is spin up and spin down along that direction in space, what are they?
Cosine of theta over 2.
Cosine theta over 2. So this thing is represented by some polar angles. That represents where that direction is. And this guy is cos theta over 2 spin up, plus e to the I phi sine phi theta over 2 spin down. And this guy is sine theta over 2 spin up, minus e to the I phi sine theta over 2 spin down. Right? Oh, cosine. Not right. Not right. So, here's my unit vector. It's written somewhere. Here it is. Ooh. My unit vector has a z component and it has a transverse component. I need to know what are the polar angles that define that direction. So I got to do a little geometry, right? If I have a vector that is pointing in some direction, it has a theta, which is related to its z component, and it has a phi. So what is theta here? Well, theta is if I think about it, it has a z component and a transverse component. The theta is the arctangent of the transverse over the z component, right? So the theta angle here, the tangent of theta, is equal to omega over minus delta. Right? Just thinking about SOHCAHTOA, that's the way I learned. You know about SOHCAHTOA? Never. I was sine opposite and adjacent. Anyway.
This cosine theta equals minus delta over omega equal to?
So this angle, I could think about this in terms of the cosine, the sine, but if I call this is my guy, there's a minus delta here and omega, then the tangent of that is the easiest thing to write, okay? When delta is 0, what's theta?
Tan inverse of
In tangent of infinity, it's pi over 2. Oh God, trigonometry, right? And when delta is really, really big, so when delta is 0, this angle is pi over 2, and then I have an equal superposition that's 1 over root 2, 1 over root 2, with a phase that depends, right? So when delta is much, much bigger than omega in magnitude, well then, this is a small number, in which case I would say tan theta is approximately equal to theta. Okay? And the sine of theta is, this thing for small theta is approximately 1 to first order, and this thing is approximately theta over 2. So this guy would be spin up along z with a little bit of spin down mixed in. And the other guy would be, in this case, a little bit of spin, mostly spin down with, that's a plus. So when I'm far off resonance, my eigenstates are mostly the bare states with a little bit, what we call an admixture. It's really a superposition of the other things. We can get this, and we'll do it, using perturbation theory. Using perturbation theory, I can also find the new eigenvectors by saying my interaction was small. If I'm very, very far off resonance, my interaction is small, and my eigenvectors are mostly this. Yeah?
Why is it a plus on the spin up? Because sine of theta over 2 becomes omega over negative delta.
Yeah, it's omega, I'm sorry, this should be, I didn't get my, that's over minus delta. Yeah, yeah.
Now, when we were far detuned, whether we were blue or red detuned seemed to matter when we pick our eigenvectors and our eigenvalues, right? When we're
What we call the excited state and what we call the ground
Exactly.
state matters. Yeah.
now when we're very when delta is essentially approaching epsilon, does that direction still matter?
Let's repeat it. When what?
When delta gets very small.
Yeah, it does. Depends. So it matters in the sense of how I approach this.
The idea that
Right. If I approach the system from the red or the blue, I move along a different curve.
okay.
Yeah.
Okay. Thank you.
If I wanted to look up that graph,
Yeah.
what are the keywords?
Avoided crossing. This is an example of an avoided crossing. This would cross if I was on resonance, but because interaction, those eigenvalues repel one another. This is an example of an avoided crossing. And it is a very important story in thinking about perturbed eigenvalues when I have a two-level system. Yes, Nate?
Is it just a coincidence that it looks like a Gaussian beam?
Oh, that's totally, yeah. I mean, it's just, they're both hyperbolas, but really that's a complete coincidence, yeah. So, I said about perturbation theory in terms of the, how the eigenvectors are perturbed by the interaction. We can also think about how the eigenvalues are perturbed. That's to say, in the absence of the interaction, the dotted line is the eigenvalues. In the presence of the interaction, I get a shift. The energy levels are shifted. So we should just maybe write this down over here. So when we had, let's say that I was red detuned. So my H0, we said, was in this. And my interaction Hamiltonian is this, let's say for 0 phase. Doesn't really matter, the phase doesn't affect the size of the shift, it only depends what the eigenvectors are. Okay. So if I'm red detuned, in the absence of the interaction, I have this splitting, where this is the ground state, and this is the excited state, and this is 0 energy in between. This guy goes down by h bar omega delta over 2, or up by h bar omega 2. Now I turn on the interaction. What I get is a splitting here, which is that. One goes up by this amount, and then it goes down by this amount. Okay? So I have a shift in the energy. Okay? What is the energy level shift in this case? So the shift, the energy level shift, say, for the ground state, was, this guy was minus h bar omega this over 2. That's the energy level shift. Okay? And what is that? Well, I can write this, I can factor out the square root of that, which is that. 1 plus delta squared, omega squared to the 1/2 minus h bar this over 2. I factor out this from the square root, and that's a positive number. So we can do perturbation theory. When the perturbation is small, when the strength of the Rabi frequency is small compared to the detuning, then this is approximately equal to using the binomial theorem. 1 plus 1/2 of that is 1/4. Okay? This energy level shift is we can think about as how we perturb the energy by the driving. Okay? So, we're going to talk about all of these things in much more detail soon when we think about the two-level atom, but this is also known in the context of driving with a laser on a two-level atom as the light shift. The shift in the energy due to the fact that we've applied light far off resonance. We've shifted the energy levels. We don't just drive the system from the ground state to excited state, we also perturb the energy levels because of the forces that we've applied to the system. We've shifted the energy levels. Okay. Yes.
When you did that approximation, you assumed omega was much more smaller than delta.
The magnitude
Oh,
delta.
I see.
Yeah.
Okay.
Yeah, I do. Otherwise, it's a more general expression. So that's really in this regime. It's how much this dotted line is shifted. This solid line is shifted relative to the dotted line by this amount. Okay. All right. Okay, there's one last piece of the story about this general problem of spin magnetic resonance that I want to talk about. And that has to do with something that's very important called the rotating wave approximation. Sometimes known as the RWA. Now, there was no approximation at all that we made so far. So we solved this problem exactly. We went into the rotating frame. There was no approximation. We had a static Hamiltonian. We were able to exponentiate it. We did it. Why do we need some approximation? Well, suppose I go back to the original problem. I have my static magnetic field here. But instead of, and we know that if we had some spin, it would precess at omega naught. And we cause this thing to flip by applying an oscillating transverse field. And the strength of that could be tiny. As long as if it was on resonance, it would accumulate and cause this thing to flip. Now, we did that by going into, we had a rotating magnetic field. But instead of a rotating magnetic field, let's say I had a linearly oscillating magnetic field that only had an X component and didn't have a Y component. Would that be enough to cause this thing to do it? And at what rate would this guy Larmor precess, would the spin Larmor precess, if I don't have a rotating field, but I have a linearly oscillating field? Well, the way to solve that problem is to break up the linearly oscillating thing into a component that is co-rotating and a component that is counter-rotating. So if I have a field that is oscillating along the X direction, I can break that up into two components. One that is rotating with this way, and one that's rotating that way. That is to say, this is equal to EX cosine omega t plus EY sine omega t. This is rotating around the z-axis with the right-hand rule, and this is rotating around the z-axis with the left-hand rule. Okay? So I can break up my linearly oscillating field into co-rotating with the spin, and one that's counter-rotating. If the thing is rotating around the z-axis. Now, let's think about this just mechanically, okay? Let's think about torque. If I had, this guy is spinning around here, if this thing was counter-rotating, instead of co-rotating, what would the effect of the torque on S be? This thing is going, it's spinning around, and then you have this transverse field, which it wants to torque about, but it's spinning in the opposite direction. It's gonna not do much at all, because, you know, it's like I start to rotate around, then all of a sudden it's gone. It's past me. It's only the thing that is in line with me, especially if it's weak, that's gonna cause me to flip. The other guy's, wait a minute, it just went by me, it's flipping, I'm going this way. It does almost nothing. Yeah.
Is it equivalent to very large detuning?
Not quite. It's a different story. It's not really about the detuning. It's really about, well, it's about, let's write down the Hamiltonian. Let's see what it is. If this is weak, if omega is much less than omega and omega naught, then the counter-rotating effects are going to be small. How do we see that mathematically? Okay, let's look at the Hamiltonian. Let's write down the interaction Hamiltonian in this case. That's going to be equal to, this guy is gamma h bar over 2 sigma. It's going to be h bar omega over 2 cos omega t sigma x. Okay, that's this. This is equal to that's cosine, is e to the I omega t plus e to the minus omega t over 2. And sigma x is sigma plus sigma minus. Okay, so the interaction Hamiltonian is equal to h bar omega over 4, e to the minus I omega t sigma plus e to the plus I omega t sigma minus. And then I have e to the plus I omega t sigma plus e to the minus I omega t sigma minus. I have 4 terms. When we had the rotating magnetic field, we had only this. When we have both the co-rotating, so this is the co-rotating effect, and this is the counter-rotating. Let's go into the rotating frame to see what does this Hamiltonian look like. When we went into the rotating frame, rotating with the rotating field, it was static. If we go into the rotating frame now, our field isn't static because there's also a counter-rotating term. So if I go and say, what is the interaction Hamiltonian in the rotating frame? Well, this thing becomes e to the plus I omega t, that cancels this. This thing becomes e to the minus I omega t, cancels that. But then we have twice that. This is not time independent anymore. In fact, it has very fast oscillating terms that are generally oscillating much faster than anything else if this is true. So if I add in, I say in the rotating frame, it's equal to this minus delta over 2 dz, then I can write down the Schrodinger equation for the amplitudes in spin up and spin down with a matrix representation. And when I write down those differential equations, what I find is the following. So this is the Schrodinger equation written in terms of the probability amplitudes. When I had a static magnetic field, these terms were gone. And I could solve a differential equation. It's another way to solve the Schrodinger equation. We did it in a very fancy way, using the rotation operator. But we could have solved this differential equation. We could just decouple these and we get exactly the same thing. I challenge you to do that. But now I ask you, in the conclusion of this lecture, how would you solve this differential equation?
Get rid of e to the 2I omega t.
I mean, this is an ODE with time-dependent coefficients. That's you can't solve, those generally are hard differential equations to solve. In fact, they generally are chaotic and all kinds of things you really have a hard time solving. Go back to your differential equations text and you try to solve a time-dependent, if you don't have constant coefficients, it's hard to solve that problem. However, if the rate of oscillation of this is much bigger than the strength of these coefficients, we can approximately solve that by something called the method of averages. And the first order, you just take the time average of it, and those terms go away. Another way of saying is that these terms are so oscillating so fast compared to the amplitudes, I only see their average effect. On average, they're 0. And that's the rotating wave approximation. The rotating wave approximation says that I just can neglect the fast oscillating terms. And then it's just like I had for the static case, but I only keep the co-rotating term. That's the rotating wave approximation. And the rotating wave approximation requires this. It requires that the rotating wave approximation requires that these coefficients are tiny compared to this. And as we will see, in quantum optics, the rotating wave approximation is an excellent approximation, because the frequencies of the drive that we're talking about are optical frequencies. They're 10 to the 15 hertz, whereas the Rabi frequencies are like megahertz. They're like 10 to the 6 hertz. So we never worry about the rotating wave approximation in quantum optics in that case. We'll come back to that next time. I've got to get out of the room for the next. I'll take any questions outside.
Looks like Pac-Man's eating your
Oh,
co-rotating.
yeah.
Waka waka.
Yeah.